Okay, so I'm trying to figure out my 3 screens here. Okay, so we'll have the chat box here in front of me. All right, let's see. Okay, we do have most everybody. We'll get started. So, hello everybody. I hope everybody had a nice and relaxing break. And we're back. It's kind of awkward to teach from the office for me, but here we go. So just to, I want to finish up the protein separation characterization lecture today and move on to pH and titratable acidity, which will be the subject of our virtual lab next week. So I know it's been 4 or 5 days and I kind of had to remember myself where I was. And we were talking about different methods of protein separation. And we started talking about electrophoresis and we stopped there. But I wanted to bring this question up to see where we at in remembering some of the separation techniques we talked about. Chromatography, we talked about salting out, we talked about size exclusion. So let's think about this question together. So in this question, there is a mixture of proteins and we want to separate. So there are 3 proteins in a mixture and I want to specifically separate protein X that has a molecular weight of 90 kilodalton and has a net positive charge of +5 at pH 7. And this protein is mixed with protein Y that has a molecular weight of 30 kilodalton, but same net charge of +5. And there is a protein Z that has the same molecular weight or very similar molecular weight to protein X, but has a +2 net charge at pH 7. Which of the following techniques would you go with to separate protein X from Y and Z? So give it a thought. Oh, Chrissy already said A. I'd like the others to think about it. I see C, F, B not sure, E, all sorts of questions, all sorts of answers. Nobody picked the right answer though. No, not yet. Coleman, good guess, but no. Actually, yes. So the only one left is G, right? So it's all of the above. Now let's think about it together. So cation exchange, meaning we're using ion exchange chromatography to separate positively charged molecules. And we have all of these proteins are positively charged. So with cation exchange, I can for sure separate protein Z from the other two because it has +2 charge, so it will leave the column sooner than the other two. And then I'll have X and Y together that will be coeluting potentially because they have similar net charge. So I can follow with size exclusion. They're very widely separated in molecular weight and I can separate them. So A is correct. Now let's look at B. I can for sure use salting out because I can put some salt concentration that will precipitate protein Z, which has the lower charge, like, and the other two will remain in solution. And then I can separate them by membrane filtration. I can use, let's say, a cutoff of 40 kilodalton or 50 kilodalton. I can remove the 30 kilodalton. It can go through the pores, whereas the 90 kilodalton will be my retentate. So I can do that. I can also do C, which I can do size exclusion first. It doesn't matter the order. I can separate first with size exclusion, separating the X and Z, they will be together. They will elute first together, and then I can, the 30 kilodalton will elute later. So I can separate them that way, and then take the first fraction that comes off the column that has my X and Z, and then run cation exchange and separate it that way. So basically here what I'm saying is there are multiple ways of doing that. As long as you systematically choose the correct combination. You can't use anion exchange, for example. It's better to use cation exchange, since I'm telling you they're positively charged. And also, it doesn't matter what the order you would. Basically, this is what the question is giving you, is that the order doesn't matter. You can start with whatever you want. Okay, and then I went on last time and started talking about electrophoresis, which is a very common technique we use to look at proteins that are in a mixture. And usually, if we look at an isolate, a protein isolate or a concentrate, it's not made up of only one protein. It has multiple proteins in it. So if we run them on a gel, we can see what components there are within the protein. We can see if they are polymerized. So let's say here, the higher molecular weight doesn't go as far down in the gel as lower molecular weight, because especially in STS page, we're separating only based on size. So the smaller molecular weights will go down more than the larger ones. So with STS page, the STS, as I said last time, it denatures the protein by breaking non-covalent bonds and giving a net charge of negative charge to the protein. So when we run a current, the proteins are going to go from the negative to the positive. So they would go all in one direction down the gel, and they separate based on size because the gel is made out of acrylamide and it has pores. So I separate the proteins. The larger ones will be on the top and the smaller ones will be at the bottom. So it's very commonly used to look at differences in protein components between different mixes of proteins, looking at hydrolysis by the enzymes, which enzyme might target what subunits. These two lanes, for example, are hydrolysates, and each enzyme here used, one enzyme targeted these fractions of proteins, and you don't see them anymore and you see smaller peptides, whereas another enzyme targeted these fractions and you don't see them anymore and you see smaller peptides. So this example is looking at enzyme selectivity, but we can also look at effective processing. If a protein is polymerized by covalent linkages due to processing, we see dark banding on the top here of the gel. So urea gel is often used when we have proteins that have similar molecular weights. We use this, as I said last time, for casein proteins. We separate based on charge to size ratio. Native, it's not very used because you don't use any detergent, and the protein, no bonds are broken, so they hardly migrate. Usually, if you have a protein in quaternary structure, they won't separate. The subunits won't separate. You don't see much of any profiling. Again, Here I showed you last time we can purchase them pre-made gels in a plastic cassette. So the gel would be solidified in within the two plastic plates. And we have wells here. We remove this comb-like structure, and in each well, individual well, we inject a few microliters of a sample, and then we put them in such a compartment here. We add a running buffer. We hook it to vol- source of current, and we run voltage. And what happens here is the protein will start migrating down the gel based on their size. And the protein will not be seen after running the gel. We break the plates and we look at this clear gel here. You don't see the proteins. We need to add a dye that would specifically bind to protein, nothing else. So we take the gel out and we add Comasi blue dye and leave it for an hour or so. And then we remove the dye and we add specific, we call it destain solution. And we destain the gel, what ends up to be a clear gel again with only the protein stained. So you can see only the protein. So it's pretty neat technique. So electrophoresis can also be done based on isoelectric point of the protein. So that means separating them based on the pH at which they don't have any charge. So the way this works is, again, we use a polyacrylamide gel, or not necessarily polyacrylamide, it can be agarose gel as well, but the mode of separation in this case is based on charge. So what we do here is we create what we call a pH gradient. So we use amphilides, which are small polymers that carry positive and negative charges. So we spot them on the gel before we load the sample, and we run a current. So we apply a voltage basically, and these pluses and minuses will start moving based on their charge. So the positive charged ones will move towards the negative anode, and then the negative charge will go to the positive um, cathode. So, so they would move based on their charges, and they settle at some point. They settle in the gel at different locations. So we created a pH gradient across this little piece of gel. Then we load the sample, and the sample, once we load the sample, we run a current again, and the protein starts moving until they reach their isoelectric point. So they reach a point in the gel where the pH is the isoelectric point of that protein. That means the protein will precipitate, will no longer move anywhere. It carries no charge. It will just stay there. And we again stain the proteins, and we will see them um, along that piece of gel. However, oftentimes the isoelectric focusing is coupled with STS page, and that is a 2D gel. The reason we do that is to get even more separation of the protein, because some proteins share the same molecular weight but have different charge, or they might have the same charge but have different molecular weight. So, so these are proteins, for example, that separated here based on their isoelectric point. We take this strip of gel and then we place it on top of a gel in a cassette that we pre-purchased, already made, and has only one well, one longitudinal well, that where the first piece of isoelectric focusing gel can fit nicely on top of that uh, SDS page gel. And we run a current. When we run a current, those proteins will start moving down the gel based on their size and separate. So if you see this example here, that blue band here, when it appeared as if it's one protein, but when we ran it down the gel, it separated into two different proteins that have different molecular weight. Whereas these two that were separated here had similar molecular weight. So if we did not separate them by isoelectric focusing, they would show up as one band or one spot. So the 2D electrophoresis helps with better separation of our proteins. Capillary electrophoresis is a technique that can be used for quantification, not only separation, but also quantitating the different proteins in a matrix. So in this apparatus, we have a capillary tube. In the capillary tube, it can be a capillary zone. That means you only have negatively charged silanol groups, so silica, basically. The capillary tube is made of silica, and you only have negatively charged silanol groups, so the proteins will separate based on their interaction with the negatively charged silanol groups, and then they separate. And basically, you also have a buffer, and you run a voltage, and they move from positive to negative or negative to positive, depending on their charge, and they separate, and there will be a detector similar to an HPLC detector where you can get a signal. Maybe if it's a UV detector, then you get an absorption value, and you can calculate the area under the curve, and if you have standards, you can get concentrations. The capillary tube can be also filled with a gel, an acrylamide gel. So it's same as a regular SDS page, and then the proteins will separate based on size. Or you can have a gel with amphilites where the proteins also separate based on their charge and their isoelectric point. So there are different capillaries that can be used to separate different proteins. Okay, I'm continuing. If you have questions, I'm looking at the chat. Please do ask questions. Next here, looking at protein characterization, looking at the quality of the protein, the nutritional quality of the protein. So with nutritional quality, we look first at amino acid composition because it tells us how much essential amino acids are present in the protein. So if we have all 9 essential amino acids, then this in the required amount, then we call this a complete protein. But other than having essential amino acids, what's very important is, can we digest this protein? How digestible that protein, and different proteins have different digestibility based on their quaternary and tertiary structure. That means how they are formed in a way that the enzymes are accessible or have access to different peptide bonds to break them. And also another point we look at the protein nutritional quality is also linked to some anti-nutrient factors. So we have enzyme inhibitors that are proteins, and if they're present, they inhibit uh, protein digestion, for example, such as trypsin inhibitor, which is a protein in soy that if we consume it, it will inhibit or limit the digestion of proteins as we consume them, and then that cause digestive problems. Lectins, for example, is another type of protein if consumed, and it's also present in beans, especially raw beans. Lectins in raw beans can cause issues in our digestive tract. Again, some inflammation and in the intestine. So these are anti-nutritional factors that are proteins. So if we look at amino acid analysis to look at the composition and the different amounts of essential amino acids, so What we want to do is we want to hydrolyze the protein into amino acids. So we want to break all the peptide bonds so that we free the amino acid, then we analyze the concentration of each amino acid. So the common way of doing that is you take your protein and you hydrolyze it with a strong acid. HCl is a commonly used acid to hydrolyze the protein. And we heat it and we digest over 24 hours or sometimes more, longer. So when we hydrolyze, then we break down all the peptide bonds and then we only have amino acids. The amino acids in this mixture then needs to be separated. So they need to be separated by chromatography. So you can either use ion exchange chromatography or reverse phase. The most common one is reverse phase liquid chromatography. You separate the amino acids, you have standards that you run, so you have standard curves so you can get concentration for each amino acid. However, not every amino acid absorbs light, so we cannot just separate and link to a UV detector. Only 3 amino acids absorb light naturally. This is tryptophan, tyrosine, and phenylalanine. So in order to be able to quantitate them and have a signal using UV detection or fluorescence detection, we react them with a reagent to give them a chromophore. To become a chromophore that absorb light or a chromophore that can also fluoresce. So we can either react them with ninhydrin. After we hydrolyze, the amino acids can be reacted with ninhydrin or also with um, OPA reagent, which is phthalaldehyde. I just call it OPA. And we measure absorption or a fluorescence even. In terms of getting the not just the amino acid composition, but also the entire nutritional quality, there are 2 assays that are common, PDCAS and PER. So PDCAS stands for Protein Digestibility Corrected Amino Acid Score. So in this assay, or this score, is basically a combination of amino acid score and percent digestibility. The amino acid score here is looking at amount of first limiting amino acid in 1 gram of test protein. When we say first limiting amino acid, that means the essential amino acid present in the least amount. So first limiting. And we compare that, we take the ratio in comparison to a reference protein. Normally your reference protein is casein because it is a complete protein. It has all of the essential amino acid in the amount that is required by the body. So we get the score, and usually the score is in between 0 and 1. And the higher the score, obviously, the better, the more complete is your protein. Now, we need to get protein digestibility, and how we get that, normally it is an in vivo assay. This is the approved, at least, method is an in vivo assay, which is basically based on having rats that get fed protein in their diet, either the protein that is the test protein or a reference protein. So you would have a group that is being fed the reference protein and a group that is being fed the test protein. And to determine true digestibility, we have to get the amount of nitrogen absorbed by the animal. So we basically look at the amount of nitrogen that did not get absorbed in the feces of the animal, and then determine how much of that nitrogen got absorbed from the total amount that was taken by the animal. So nitrogen absorbed over nitrogen intake, and we get a percentage there. And then the PDCAS is the amino acid score, and multiplied by the percentage of the true digestibility. So again, you get a value between 0 and 1. So if you get a value of 1, that means all of the protein is digestible, 100% digestible, and it has amino acid score of 1. Now, why is this important? This is important because that's the value used, the PDCAS is used to determine percent daily value of protein on the nutrition labeling. So you take the grams of protein per serving, and to determine percent daily value, you don't just divide it by 50 grams of protein, which is 50 grams is the required amount per day, or the average required amount of protein per day. You don't just divide that and multiply by 100 and you get percent daily value. You have to take into account the PDCAS score, because depending on the PDCAS, this protein might not be available 100%. So if you have 15 grams or 10, let's say 10 grams to make the math easier, and you have a PDCAS of zero 0.8, that means only 8 grams are available. So that would be 8 divided by 50 times 100, then you'll get your percent daily value. PER is protein efficiency ratio, and this is actually used here in the US only for infant baby food or infant food, not for children and adults. However, in Canada, they use PER, they do not use PDCAS yet. So PER, why is it only used for infant food? Because it's really based on the weight gain of baby rats or small rats. So what they do is they feed those animals the test protein and then the reference protein, which is usually casein again. And so then they take the weight of the animal over time, and obviously the baby rats will grow over time, and then they will relate how much weight they gained based on how much protein they consumed. And they get the PER and they correct it by the PER of casein as well. And that is also a value relative between 0 and 1. Other tests that can be done is looking at essential amino acid index. Here you calculate all of the essential amino acids. You determine all of the essential amino acid amounts and you get an index. And there's also the in vitro protein digestibility. So there are kits out there that can determine protein digestibility based on using digestive enzymes. And instead of doing the in vivo assay, you basically determine digestibility in vitro by mixing the protein with a series of enzymes that are present across our digestive tract. And then monitor the hydrolysis of the protein over time. So you can monitor by determining the change in pH over time and use that in an equation, or you can maintain the pH. So make sure that you continuously add acid or base to maintain the pH at whatever is the pH. And then you determine how much volume of a base you've used, for example, because as you hydrolyze the protein, amino acids are released and the pH drops. And then if you constantly add NaOH to keep the pH where it was, you can get the volume of NaOH at the end and use it in an equation to get the percent hydrolysis. Lastly, here's the lysine availability. Lysine is an important essential amino acid, and it does get destructed during processing, especially when we potentially have reducing sugars, where you can get reaction with reducing sugar and you lose lysine due to Maillard reaction. So there are specific assays where you look at loss of lysine. For example, you just specifically measure the epsilon amino group, which is the amino group in the R chain, which is directly related to the lysine presence. You can react that amino group with fluorodinitrosobenzene is the reagent, and you get a chromophore that absorbs light or fluoresce. Lastly, protein characterization you can also look at the functionality of the protein by measuring solubility, emulsification, foaming, gelation, or viscoelastic properties if it's specifically gluten proteins. But these are not going to be covered in food analysis. So there would be, they used to be subject of another class which got canceled. But anyway, so these are important characteristics for protein because protein ingredients are used for their functionality. So looking at different protein ingredients and how they can function in different food matrices, we look at their functional properties that way. Okay, so that ends this section. Are you all with me or you fell asleep? Okay, I hope you're here still. Okay, I'm going to exit this and start sharing the next topic. pH and titratable acidity. So let's have some interaction here a little bit. So this is going to be the subject of, like I said, the last virtual lab. Let's see what we know about organic acids or food acids. They are weak acids, they have good buffering capacity, they can buffer at multiple pH. Okay, I'm getting G or D. Oh, I got E too. Okay, so a mix of answers between G, E, or D. All right, so food acids or organic acid are weak acids. So can you tell me what defines a weak acid versus a strong acid? What makes an acid weak versus strong? Anybody remember that from maybe organic chemistry? Aha, yes. Thank you. Complete dissociation in water. So strong acid dissociate. That means you will find H plus and the rest of the acid, whatever it is. If it's HCl, it would be in water, it would be H plus Cl minus, completely dissociated. Whereas weak acids, they're partially dissociated, almost only like 3% dissociated. That means most of the acid still has the H holding on to it. So you have HA, that means non-dissociated acid. This is a common term. HA, non-dissociated acid, or A minus, dissociated acid, where the acid gave up its proton already. So organic acids are weak acids. That's what makes them have good buffering capacity. So they're able to give their protons and they're able to pick up protons. So basically, depending on changes in pH, if the pH is reduced, they will pick up a proton. If the pH is increased, they will offer up a proton. That's what makes them good buffers. And can they buffer at multiple pH? So those of you that said G, can you tell me why you think they can buffer at multiple pHs? What's in their structure that allows them to buffer at multiple pHs? Okay, so those of you that guess G, just because? Kat, you're close. They have multiple carboxyl groups. So For example, citric acid has three carboxyl groups. Carboxyl groups are the COOH. So if you have more than one carboxyl group, that means that you have three different pKa's, or constant of dissociation. So what pKa is the negative log constant of dissociation. But since you have different carboxyl groups, then they can give up hydrogen at different pHs, depending on the dissociation of the proton in each position. So citric acid has three carboxyl groups, so it buffers at three pHs because it has three pKa's. And acidic acid, for example, has one carboxyl group, so it buffers only at one pH. So depending on how many carboxyl groups or how many protons they can give at different locations in their structure. So can you tell me what the pKa? I've been talking about pKa. I just want to make sure you know what pKa is. What is pKa? Yeah, it is negative log of Ka. Yes, but what is it? Um, mm, it has a different definition. It is related to the strength of. If you want to link it to pH, how would you link it to pH? Yes, but if you want to link it to pH, what's the relationship? Not really. You gotta remember you gotta remember it's been a while that we talked about buffers at the beginning of the semester. Yes. Yes. So pH equal pKa plus log of concentration of conjugate base over concentration of acid. But in simple way, it is the pH where you have equal concentration of dissociated acid and non-dissociated acid. So when you have 50% as A minus and 50% as HA, then log of that ratio is 1. Then pH equal pKa. So that's at maximum buffering capacity, basically. That is what pKa. pKa is the pH at which you have 50% of the acid dissociated and 50% non-dissociated. Okay. Mm. Oops. So let's look at this now. Two drinks with the same pH, do they have the same titratable acidity but different sourness intensity? True, false, and tell me why. B. Yeah, it is. Yeah, so those of you that are saying false, why do you say false? Okay, so I'll explain that. You don't have to. You can have the same pH, but actually different titratable acidity. That's because of the difference in dissociation of different acids. Because depending on the acid you have, you can have an acid that is more dissociated than another. And pH is the measure of active or free hydrogen ions. So at same titratable acidity, or let's say at same concentration of the acid, one acid would be completely dissociated, so the pH would be much lower than another acid that is partially dissociated. So this is a false statement. So if we look here, so what is titratable acidity? It's basically the concentration of the acid. And it's called titratable acidity because we're measuring the concentration of the acid, of the total acid, by titration. So we basically titrate with base when we measure acidity. And when you titrate with base, you're giving OH minus to your solution, to your acid in the solution. So as you titrate with NaOH, your non-dissociated acid will give protons, and you continue titrating until there is no more carboxyl groups with protons. So the next drop of NaOH will change the pH rapidly. So there's no longer resistance in changing of pH because all of your carboxyl group gave up their hydrogen, and then you can get, you do an equilibrium equation and you get titratable acidity. So it's the total acid concentration. You continue titration until no more carboxyl groups have their protons to give. So it's basically a measure of total acidity, and it affects the flavor, and it is an indicator of maturity. Why? Especially in fruits. So as the fruit ripens, the acid concentration goes down and the sugar concentration goes up. So titratable acidity is therefore an indication of maturity. If we look at pH, on the other hand, it's a measure of the free hydrogen ions. So free hydrogen ion or dissociated, that are dissociated from the acid, they bind in water, they bind to water, and they give you what is we call hydronium ion. So H3O plus is hydronium ion. And that's what gets measured by the pH or pH meter when we're measuring pH. So it's a measure of active acidity. So that means the free protons they are correlated with active acidity. They have pH has different implications in food. They affect different reactions in food. Can you name some reactions that might be impacted by the pH of the system, which impact perishability, impact structure, flavor, lipid oxidation? Okay, yes, pH can impact lipid oxidation. Basically, it can impact chemical reactions. One, it can impact Maillard reaction at slightly alkaline pH. You enhance Maillard reaction. Yes, it impacts structure of the proteins, definitely. Taste, yes. Microbial, exactly, microbial growth. So what I'm looking here for is some of these reactions, chemical reactions, microbial growth. There's one more that is very important in food, a specific type of reaction. Let's see if anybody's gonna, yes, thank you, Michelle. Enzymatic reaction. So pH can impact these main ones, chemical reactions, microbial reactions or growth, and enzymatic reactions. So pH is very important. And also in food, it impacts how we thermally process the food. So acidic food, for example, anything less than pH 4.6 requires milder thermal treatment to pasteurize, because you don't get those you can get rid of pathogen bacteria when the pH is low, and a combination of low thermal treatment. However, when the pH is above 4.6, we need higher thermal treatment to pasteurize the food or inhibit pathogen and spoilage microorganisms. Okay, so here's again looking at titratable acidity or total concentration of acid versus pH. So there's here two acids. You have acetic acid and you have HCl. Acetic acid is an organic acid, so it is a weak acid, and HCl is a strong acid. So, and at the same concentration, 0.1 normal, same concentration, so the HCl is going to dissociate completely, fully dissociate, and gives you a very low pH of 1.02. whereas acidic acid is going to partially dissociate and gives you a higher pH, more than double, almost triple, pH 2.89. So here's just a literal example of having two solutions or acids at the same concentration, yet they have different pH. So that's an illustration of a strong acid versus a weak acid. Okay, so here I'm pointing out to your conjugate base. So when the acid is dissociated, then you have your active proton, and then you have the dissociated acid that is also known as conjugate base. So that you want to remember, because when I show the again, the Henderson-Hasselbalch equation, I will refer to that A minus 2. I will refer to it as conjugate base. So just want to remember that. Okay. I have few more minutes. I will skip this. I'll bring it back on Wednesday. So acid is a proton donor. So that's the basic definition of an acid, is a proton donor, and base is a proton acceptor. So basically acid readily gives you its hydrogen and forms in water hydronium ion, whereas the base accepts the proton and forms hydroxide ions in water. So in the neutralization equation, which is very important for titratable acidity, you have an acid and a base, and you end up with salt and water. So if you have equi concentration of acid and base, you have the water with a pH of 7, right? So where did that pH of 7 come from? It came from this Kw, which is the ion product constant for water, which is basically the concentration of hydronium ion multiplied by the concentration of hydroxide ions. So at 25 degrees C, it's impacted by temperature. pH is impacted by temperature. You have to remember that. Um, at 25, which is room temperature, you have approximately 1 times 10 to the minus 14 as the constant. And the span of pH is 1 to 14, right? So here's your pH 7. So at pH 7, you have equiconcentration. You have 1 times the concentration of hydronium ion is 1 times 10 to the negative 7, and the concentration of OH minus is 1 times to the negative 10 to the negative 7. So pH is basically the negative log of hydronium ion concentration. The negative log of 1 times 10 to the negative 7 is 7, and that is the pH of water. So when we have equiconcentrations of hydronium ion and hydroxide ion, you have a pH of 7. Okay, so we can stop here actually, because what I want you to do next time when we come back on Wednesday, we need to do some calculations together for extra credit. So prepare yourself next time with a piece of paper to start. You can also start thinking about it if you like, and we'll do the calculations together in class next on Wednesday. All right, well, I'll see you all on Wednesday.
And can I ask you a question about the paper?
About the paper?
Yeah, it's not,
Yeah.
it doesn't have to do with this.
Okay, what paper?
The approximate lab report.
Oh, the report. Okay, yes. Let me just stop recording here, and we can have people leave if they want to.